programming. The purpose behind this talk and the book that I wrote called Functional Thinking, a lot of times when you start looking at functional programming, you're also looking at a functional programming language, and the syntax and the meaning sort of get mixed up together. The functional concepts are really important regardless of what syntax you use to get to those functional concepts, and that's really what I'm focusing on in this talk. So I try to show examples in languages as close to ones that you're going to be familiar with as possible. So I try to stay in the Java family with Java and Groovy, and then if I need to show something that is beyond its capabilities, I'll do a little bit of Clojure and a little bit of Scala, but I'm trying to focus here on the concepts of functional programming rather than the specific syntax. And so here's my agenda. I'm going to talk about 4 different aspects of functional programming, but I'm going to start with a metaphor and a history lesson. And here's the metaphor. So let's say that you're a lumberjack and you're okay. And you're the best lumberjack in the forest at cutting down trees with an axe. It's stunning how fast you can cut down trees with an axe. And then someone comes along and shows you one of these, but they don't show you how to use it. And so your first instinct as a lumberjack is take the uncranked chainsaw and swing it against a tree, and then very quickly reach the conclusion that this is a terrible way to cut down trees. I'm going back to my axe. Because I've been using this axe for 10 years, feels really good in my hands, really nice and familiar. There can't be a better way to cut down trees than an axe, right? And then someone shows you how to crank this, and obviously you get way more productive. The point of this is, learning a new syntax is easy. We've all done this many, many times in our careers. But learning to approach problems in a different way is really hard. And that's really what I'm trying to get at in my book, in this talk, is learning to think about seeing problems in a different way. And so the point of this is, of course, that functional is much more a way of thinking rather than a language or a framework or a tool. And you can actually do this in any language. Some languages make this easier than others, but you can really do this in any language. So here is the history lesson. This is something you can download from O'Reilly's website. This is a brief history of computer programming languages. It's brief in that it only covers about the top 200 programming languages. There are well more than 2,000 languages we've created since we started building computer languages. But I want to talk about a certain era and back up just a little bit and crash Keynote. Oh, that's interesting. That's not what I intended to do. Let's try that again, shall we? So this is my slide of the history of computer programming languages. Like I said, you can download this from O'Reilly's website. Very interesting, but I want to go back in time just a little bit. This goes up through about 2010. I want to back up just a little bit to an earlier era, and around the 1970s and 80s, and talk about the creation of this language. Anyone know the significance of Simula 67? It's kind of famous for one reason. Anybody know that one magical reason that it's famous? It's computer science trivia. Really, no one? No, you're just too Scandinavian to say anything in a public. Okay, that's fine. Simula 67 was the very first object-oriented language. This is generally considered the father of all object-oriented languages. Simula 67, 1967. Smalltalk came along in 1971, and C++ came along in 1983. Now, a good argument could be had over drinks as to exactly when did object-oriented programming become mainstream, but certainly not before C++, which is when most people first heard of those concepts. If you go back and look at the kind of code they were writing in 1967, this is really before even the structured programming revolution. So these guys were writing computer programs with go-tos and line numbers and crazy stuff like that. And you'd think that somebody came along and showed them something as cool as objects, they would have gone, oh yeah, we should stop doing the silly stuff we're doing and start doing that right away because that's way better. But it took 15 years before those obviously good ideas sunk in and became part of the mainstream of computer science. And this happens all the time in the computer programming world, where you have a kind of mainstream of technology, and then you have offshoots, academic offshoots like functional programming, which is a way of thinking about different ways of expressing algorithms and being able to take advantage of things like multiple cores and those sorts of things. You have practical offshoots. The 4th generation languages of the 1990s are a good example of a kind of practical offshoot from this mainstream. But every once in a while, one of these offshoots comes back and rejoins into the mainstream. And that's exactly where you see functional programming now. All the major new languages have really strong functional features or are exclusively functional. Clojure and F#, very strongly functional language. Scala is a mixed paradigm language that allows you to do functional stuff. Java has functional features now. JavaScript, just about any language you're going to bump into, has really strong functional features now, for some reasons I went through during my keynote today. Now, I mentioned this quote in my keynote, but here's the actual quote. This is a really keen observation by Michael Feathers, who's well known for the book Working with Legacy Code. And his observation was that object orientation makes code understandable by encapsulating moving parts. If you think about some of the mechanisms in a language like Java, where there's a lot of control about visibility and encapsulation and information hiding, those are all built into the language very specifically for a very specific purpose, but those account for lots of moving parts. And in fact, this is part of the unit testing burden in object-oriented languages, is you're constantly mutating the state of one thing to another thing, and it makes for moving parts. Functional programming makes code understandable by minimizing moving parts and making them disappear so that if you don't have to interact with them, you can't mess them up. And the classic example of this is the way memory management works in Java. You never have to interact with that. It's just an automatic thing, and you can't really mess it up, or it's extraordinarily hard to do so. And I showed this example in my keynote as well, but this is a good example of some of what I was talking about there, what Michael Feathers was talking about, this company process. When you think about this in the pre-Lambda kind of world, you will tend to think of doing this as an iteration through something like a for loop. And even though we have 3 tasks there, we tend to do it in one for loop because it's more efficient to do it in a single for loop. But of course, when we have something like lambdas, we can take advantage of the declarativeness of functional programming and build something that's a lot closer to the problem definition that we're working on. Because it lets us capture these common kinds of operations in very terse ways, then it yields much more readable code. And as I observed in the keynote, also can very trivially be made much, much more powerful, because the people who wrote streams also took into account what it would make to make this a parallel stream and built all that in at the language, at the stream level in Java, rather than something that you have to deal with on a regular basis. There's a terrific term that Rich Hickey resurrected called complect, which I love, and I mentioned in the keynote as well. When you intertwine or braid things together, this is in fact one of the sources of complexity in software, and that's one of the things that functional programming often lets you untangle because you have better abstractions to express problems. And that is in fact the best benefit of functional programming, is it allows you to operate at this higher level of abstraction. But let me look at another example now, and I want to talk about several examples in this problem space. If I want to talk about different programming styles, and I need a problem to program around, and so I've chosen this one of number classification. This is something that an ancient Greek mathematician cooked up, this idea of a perfect number. So if you take the factors of a number, the factors are the whole numbers that when multiplied together equal the number. So 6, for example, has 4 factors, 1, 6, and 2 and 3, because 1 times 6 is 6 and 2 times 3 is 6. And so what this Greek mathematician figured out is this weird characteristic of numbers, that if you take the sum of the factors and add them all up, and there are some numbers, if you take the sum of the factors and add them up and then subtract the number itself, you end up with the number. And 6 is one of those numbers. If you take the sum of the factors and then minus the number itself, because the factor is one of its own, the number itself is one of its own factors, then you end up with the number. And so there's a classification scheme built around this idea of perfect numbers, where the sum of the factors equals twice the number means it's a perfect number, the sum of the factors is greater than twice the number means it's abundant, and the sum of the factors is less than twice the number means it's deficient. And so any whole number integer can be one of those things. There's another concept that makes the math part of this a little simpler, because I don't really care about the math, I'm more about the structure. And it's this idea of an Alloy sum. The Alloy sum is the sum of the factors of a number minus the number. And you'll notice that's exactly the formula for something like a perfect number. So you can shorten this formula to say if the Alloy sum equals the number, then it's perfect. If it's greater than the number, it's abundant, etc. So let's look at several different ways of implementing this behavior. And the first one I'm going to show you is a purely imperative object-oriented version. And in fact, it was the example that I used in my book, The Productive Programmer, as an illustration of doing test-driven development and the impact that test-driven development has on design. So if you're interested in the full derivation of how this code came to be in the shape that it is, that is actually the free sample chapter from my Productive Programmer book. But here is that code that manages number classification in an imperative style. And I'll talk about this in turn. So this is my imperative number classifier. I have two pieces of state that I hold on to here. One is the number itself, which makes writing unit tests easier because I can pass it around as parameters. The other is a cache, because what I'm doing here, one of the things I'm going to have to do as part of my solution for number classification is sum all the factors together. And the way that I've set this up is I have an isPerfect method, an isAbundant method, and isDeficient. And if I get a number, I may ask, is it perfect? And if it comes back as not, then I may ask it, well, is it deficient? Meaning I have to sum the numbers, the same number multiple times. And I don't want to have to do that, so I'm going to cache the sums. So that the first time I encounter a number, I'll cache it so I don't have to recalculate it again. That's what that cache is there for. In my constructor, I initialize my two things. Here is the method that really does the work for finding factors for me using the mod operator in Java, because if candidate goes into number with 0 remainder, that means that candidate is a factor of number, and so isFactor will return true for that candidate. And here's the code that actually goes and fetches all those factors. I create a new hash set, add 1 and the number to it, because those are always factors of the number. And now I'm going to iterate through these guys up to the square root of the number. I'm taking advantage of a really common optimization here, because I could go through every single number, but it's inefficient to do that because I can always make the observation that factors come in pairs. So for example, if I'm looking after the target number for 16, when I grab the factor 2, I can also grab 8 because 2 times 8 is equal to 16. And so I really only have to loop as far as the square root of the number and be able to grab all the factors that way. And so that's exactly what I'm doing here, is only looping up to the square root of the number and then grabbing both factors at the same time. That is, in fact, why I'm keeping these guys in a set, to keep duplications down, because a duplication can creep in if you keep this in a list. Here's my method that calculates the alloy sum. All it does is iterate through the factors and sum them all up. And then here is my cached alloy sum, which uses my cache, calculates it, and puts it in the cache the first time it sees it, otherwise returns it from the cache. And then finally, my 3 candidate methods, isPerfect, isAbundant, and isDeficient. Just take advantage of that alloy sum method and check equals, greater than, or less than. So that's the imperative version of this code. And notice it has a little bit of internal state here, and that makes it more testable, and it also allows me to have that lazy initialization of my cache. It also makes it very cohesive in that every one of these methods is very small and just does one single thing. It's very composed in the Kent-Beck composed method style of coding. It's very testable. In fact, it was written as an example of testability. But it also uses mutable state and a bunch of other stuff that we try to get away from in the functional programming world. So let's look at what a functional version would look like in Java 8. And here's the functional version by number classifier, and virtually all the complexity is just melted away. And now, instead of returning a list, I'm returning a stream when I get factors of, and here I can just say range from 1 to number plus 1, because ranges are not inclusive, filter out the ones that are not factors. And so that gives me the list of all the factors. Now for my alloy sum, I need to go through that stream of numbers and add them all up. But I just got stupidly lucky in this case, because streams in Java always have a terminal, and the terminal is the thing that causes the stream to start generating values. So one of the terminals is a collector that collects things together. We showed that terminal in my company process example. Fortunately enough, one of the terminals in Java is sum, and that's exactly what I need to do there. And so I can just say that stream.sum, and it'll give me the sum, and then I subtract the number, which gives me the alloy sum, and then there are my isPerfect, isAbundant, and isDeficient methods. However, notice that this version is not as efficient as the hand-coded imperative version, because this one doesn't do the square root trick. This one goes through every single value. I'll show you how to get the square root optimization back in a functional way in just a second, but on the surface of this one's not quite as efficient because I'm not down in the internals of how things work, and so it might be a little less obvious here how you might perform that optimization. But I'll show you the optimized version of this in just a second. And again, this is toward that idea that functional programming allows you to operate at a higher level of abstraction. So let's talk about some building blocks in this functional programming world, because one of the common characteristics of functional programming languages is that they tend to build sophisticated functionality around existing data structures. The encouragement in the object-oriented programming world is to build brand new data structures for every problem that you encounter, whereas in the functional programming world, the goal is to let's mash problems into well-known data structures that we already have really good tools for. And these common tools are super common through functional programming languages, but one of the tricky things is they sometimes have different names in different languages, because some languages came from more of a scripting language background, some came from more functional programming background, and in fact some of these commonalities weren't even really discovered until they really started diving deep into category theory in the late 80s and 90s and actually realized the common behavior of a bunch of these things. And so I'll talk about a few of these building blocks, and one of these is filter. This is a fundamental operation that performs a Boolean test on every element in a collection and returns only those that pass, so you typically get a smaller number of things. We saw this in the Java 8 version of using filter in a functional way, where I'm filtering out those potential candidates so that I only get my list of factors. Here's the exact same code in the Scala world, where filter acts as an operator here, and the ranges in Scala is 1 to number in filter and is factor, and I don't care about this parameter, so I can just pass it as an underscore. And here's the exact same code in the Clojure world. Clojure is a list, so you kind of read things inside out, and so this is a factors function that takes in numbers a parameter. Range from 1 to number plus 1 gives me the range of numbers. That's the second argument to this filter function. The first argument is an anonymous function that, again, uses that as a replaceable parameter and determines if that's a factor or not using the same code that I used before in my Java version. So that's filter. Another one of these fundamental operations is map, which takes a given function to each element and returns a transform collection on a given collection. Here's an example of the square root optimization in Java 8 for factors of. What I'm doing here is basically what I did before, in that I'm only going up and grabbing the numbers up to the square root of the number and grabbing those and putting them in factors. Then I'm using map to map the symmetrical factor on top of all the ones before the square root to grab me the ones on top of the square root. And so this is actually the optimized version. There's a whole lot more syntax here than it seems like it would be necessary, but Java is very good at taking very simple concepts and drowning them in verbose syntax, and they've done a good job here in the functional programming world as well, because you have to do all this boxing and a bunch of stuff like that to get things to fit together. But it certainly works, and it's more elegant than the alternatives, and nowhere near as verbose and messy as things like generics in Java. And here's the exact same code, the optimized code in Groovy. Now Groovy comes from more of a scripting language background, and so in the Groovy world, instead of filter, they call it find all. But notice it still takes a code block. Anything in curly braces in Groovy is a code block, and its replaceable parameter is just the keyword it instead of the underscore or the percent sign. And in the Groovy world, instead of map, they use collect. The behavior is the same, but different terminology because it comes from a different kind of a programming background lineage. Another common operation that you find in a lot of functional programming languages are things that mash formats or nested formats into simpler formats, and flatten is a good example of that. It removes nesting from a collection of things. Here's an example in Clojure of taking several different vectors and flattening down to a single sequence. Here's the exact same behavior in the Groovy world of taking multiple nested arrays and flattening down into a single array. You can also do this on things that are collections but don't necessarily look like collections. Like, for example, the letters in a word. You can map all those, each one of them, to a list and then flatten that list, and you'll get a flat list of all the characters in a sentence. It's also common To combine two things together, you frequently in the functional programming world find that you're flattening something and then you're mapping something, and those two things go together a lot, and so you end up with a flat map, which is a composed version of that, which maps a function over a collection and flattens the results by one level. This typically just does one level instead of however many levels you have, but here's an example of a flat map in the Scala world, taking each one of those and flat mapping those down to a list. Here's an example of using characters in a string and flat mapping them in the Scala world, again, to a list. And the Clojure world, they have flat map too, but they call it mapcat, which is the more traditional name in the Lisp world, but it does the exact same thing. You can split those things up and then mapcat them into a single flattened collection. So the third of the fundamentals, so we saw filter, we saw map, and several variations. The third of these fundamental operations are reduces and folds. And reduce and fold is sometimes used interchangeably, and some languages just have one or the other, and there's a lot of overlap in the way they work. So let's talk about reduce first. Reduce uses a supplied function to combine input elements and often down to a single input value. So for example, sum is a good application of something like reduce because we take a collection and reduce it down to a single value. Here's an example of doing reduce in the Clojure world. Factors of number gives me a list of all the factors of the number. The reduce function is expecting a function here that takes two input elements and returns a single value. And notice that plus is a function that does exactly that. This can actually be any function in the Clojure world that takes in two arguments and returns a single result. And I'm reducing the factors of the number, and to calculate the Alakoi sum here, I'm taking the sum of the factors and then subtracting number from it. Notice that is the formula for my Alakoi sum. Here's the exact same code in the Groovy world, and notice here factors of number. Inject is what they call reduce or fold in the Groovy world. This is the seed value of the accumulator, which I'll talk about in a second. And notice this is a code block that takes in two parameters, returns a single result by adding them together. So that's doing the exact same thing, that same sum operation that we saw before. A very similar animal to reduce is the fold family, fold left and fold right. And again, this uses a supplied function, combine input elements, often down to a single value. And so here's an example of using fold left in Scala to sum all the factors in a list. Factors.fold left, 0 is the accumulator, and again, there's an anonymous function that takes two parameters and returns a single result, so that is the definition of a fold. And the reason this is called a fold is because it acts conceptually like this. When you have the elements in a collection, you create an accumulator, and you fold this element in on this one using this operator, and each one of those adds to the accumulator, and so you keep folding the list to the left until you're left with the value in the accumulator. So that's why this is called a fold operation on a list. They're kind of metaphorically doing that. Very few languages have a fold right for reasons that will become apparent to you very, very soon, because it does odd things. So fold right, reduce right are the similar kind of animals, and Scala has one of those. But when you run list range of 1 to 10 and reduce right and use minus, you actually end up with 5. Because what it does, it doesn't do what you might think it would do, which is take the last one and subtract the next to last one. It takes the last pair and subtracts. So in this case, this is a list from 1 to 9. So it takes 8 minus 9 to get minus 1, and then uses that, and then 7 minus that to get me 8, and then 6 minus that to get me negative 2. And so it's kind of bouncing back positive to negative until I end up at 5. Probably not the result that you wanted, and probably not something you would ever use for anything realistic in the real world. You can do fold right kind of stuff on strings and some sort of behavior like that sometimes makes more sense. But this is a very non-intuitive thing to think about what's actually going on here. So not used a lot. So having said that, there are really deep similarities between the fold versus reduce family of things. And so in both cases, both use an accumulator of some kind to accumulate the values that you're building up. And traditionally, and this is not always universally true, this is another one of those things that's not consistent across all functional programming languages, but traditionally in reduce, you supply the seed value for the accumulator, and a fold typically starts with nothing in the accumulator. You don't supply a specific value for it. And we've seen exceptions to that rule here, but in general, this is probably true that Fold starts with nothing in an implicit accumulator for some appropriate value of nothing. So if you're doing a reduce on a string, for example, nothing would be an empty string there. And then for both fold left and reduce, it uses this binary function to go through each element to combine and update the value of the accumulator. And then it keeps doing that until the list is exhausted. So here's an example of a really old challenge. John Bentley wrote this column for, I believe it was the Journals of the ACM, called Programming Pearls, which are little cool algorithmic tricks and things like that. And at one point he issued a challenge. And Donald Knuth picked up that challenge and ended up writing about it in his book called Literate Programming. And here was the challenge. Read a file of text, determine the n most frequently used words, and print out a sorted list of those words along with their frequencies. It turns out this is a little bit of a famous practical joke in the computer science world, because Donald Knuth, when he took up that challenge, was experimenting with these ideas of literate programming, and he ended up creating a 12-page algorithm to handle this problem, and ended up copywriting this algorithm as a new, unique way of solving this particular problem. And then John Bentley showed his solution, which was a 7-line shell script that actually was more efficient and performed better than the custom 12-page algorithm written in Pascal by Donald Knuth. And he freely admitted that in literate programming, that maybe he went a little overboard on the design side, that maybe there was a more elegant solution right under his nose. But it solves an interesting little, serves as an interesting little challenge for us. Because here's an example in pre-Lambda Java of doing exactly this. Going through and building up a word map, and then using regular expressions to go grab all those guys, and then getting rid of the non-words, which are the single words and prepositions and that sort of stuff, and then sticking them in a cache and returning them. Here's the same code in the Lambda version of Java, and the most complex thing here is mashing a regular expression down to a stream so that we can actually use the stream API on top of it, because the regular expressions in Java don't support streams, which would be really nice, but you can mash it down into something that does support streams, and once I get this to a stream, then I can use map and filter and those kind of operations on it. And notice that in the Java world, this is the terminal on that stream. Notice there's a get or default, which is common in a lot of functional programming languages, that gets me the value if one's there, or returns a default value if one is not. So that makes it really easy to update things. And so this is another good example of how things get much, much simpler when you can move things over to the functional programming world. And so this is the way that you tend to attack problems like this in the functional programming world. Look for opportunities to use filter to get a subset of a collection based on some sort of criteria. Use map to transform collections in place, and then use reduce or fold for piecewise collection processing. This is part of that process of shifting. When you look at a problem, think, which of these fundamental building blocks could I use to start attacking that problem, versus something like iteration. So now let's talk about working a bit smarter rather than harder, and I have two examples here, one of laziness and the other of memoization. So let's talk about memoization at first. I showed this example in my keynote, but you probably have a lot more context of understanding this now, because this is my classifier, and I'm going to build a cache for the sum. And this is in Groovy, so I'll build my sum of factors cache here by hand. The point of memoization is I never have to write that code by hand again, because I now have memoization. So as long as this is a pure function, meaning it has no side effects outside of the parameters passed inside it, then I can go in and say whatever that function is .memoize, and this returns me a function pointer that is now memoized, and the runtime is now caching all those values for me rather than me having to do that by hand. So that's a really, really nice way of not having to worry about that particular problem anymore, and in fact a good example of that eliminating moving parts idea that I was talking about before, because you never have to write a cache again. You can just rely on the language of giving you that capability the next time you need it. And in fact, this is already built in to a lot of languages. This is the memoization results I alluded to in my talk earlier this morning, where I tried really hard to handwrite a cache that performed better than the memoization in Groovy, and I didn't get anywhere close. And I make the point in my book that language designers will always be able to build more efficient mechanisms, because they do things that they have internal knowledge, and they can get to things that you can't get to, and that's probably, as I observed, a good thing. Some functional languages have memoization built in, like Clojure, for example, has memoization built in. So this is the famous Caesar cipher, where it rotates something around by 13 characters in a map. So that's a ROT13 definition, and it actually does this against that map. Now I can come in here, so it might be really inefficient to cache the values for every single letter. I don't want to have to calculate those every time, and so I can come in here and memoize that function that returns that, and it will now cache all those values for me and return them just like a handwritten cache would. So memoization is built in. You can apply this to any function in Clojure, and it will return you a memoized version of that function. You can also trivially build memoization in Java 8 with lambdas and with the code blocks in Scala. You have to make sure that your memoized functions don't have side effects and don't rely on outside information, because you're only going to execute them once now, and those values are going to be cached. And so if you have side effects that you require to run every time, it's not going to work anymore. But as long as those two things are true, you can memoize them. And in fact, you can customize the memoized behavior, memoize at most this many elements, at least this many elements, etc. Another common characteristic in functional programming languages is laziness. And the idea behind laziness is to be able to build data structures that defer expression as long as they possibly can. So the idea is to defer expensive calculations until you absolutely need them, until you really need that value. This is the way you can also do things like create infinite collections. Say you could create all the numbers in the universe as a collection and then just pull off the ones out of that set of all possible numbers that you want. And the really nice characteristic of laziness is that functions like map and filter can be made more efficient when you do lazy evaluation. So they only do work when they really need to produce results. You can get laziness in Java pre-Java 8 by using the appropriate libraries. There's a really terrific library called Totally Lazy that works for versions of Java way back, like probably Java 5 as far back. But this actually gives you lazy collections and lazy data structures on top of Java. They also use the Hamcrest matchers and write, because they can't do operator overloading, so they do some fairly verbose things for math. But this is a version of my classifier in pre-Java 8 that all the collections and everything are lazily generated using Totally Lazy. But of course in Java 8, streams are already lazy. And this is in fact one of the really nice things in Java 8 is that they've done a really good job of implementing the stream API in Java. So when you look at something like filter or map, these are part of the stream and you can attach these to something, but they don't really start producing values until they get attached to a terminal, like reduce or sum or for each that will actually collect values. So streams in Java 8 are functional rather than stateful. There's no actual state in the stream. It acts kind of like an iterator in that in an iterator there's no actual state there. It's just traversing a collection. And the same thing is true here. In fact, just like iterators, these are consumed upon use. So once you've gone through them one time, you have to regenerate the stream before you can go through them again. But they're also unbounded and infinite when they can be, and so we now have lazy streams in Java because these streams are as lazy as they can be in Java and do some other nice things like deferred evaluation. There's some real nice benefits when you have laziness built into your language, so consider this code in Groovy. This is a palindrome finder that goes in and finds palindromes and strings. And if I just care about the first palindrome here, it's going to go and find all the palindromes in the string so that it can return me the first one. Whereas if I build that same code in Clojure, it evaluates these palindromes lazily because all these data structures work lazily anyway. And so if I come down here and say just take one, my first palindrome, it'll just give me Bob and not do the extra work to generate and find out if those other palindromes exist because I don't need to know that yet. And so laziness actually causes you to do less work to achieve the same kind of computational results. Laziness in Clojure is built in at a very low level at the underlying abstraction for all sequences and lists in Clojure, the seek. This is the core of laziness, and all the collection functions here produce and consume sequence, and the concrete and lazy seeks can interoperate. And so Clojure goes a long way, and in fact probably as far on the JVM as you can go on building stuff as lazy as possible by default. Nowhere nearly as lazy as a language like Haskell where everything is lazy, but very, very far in terms of the JVM. Scala attacks laziness in a different way because in the Scala world you have regular collections. So here's the palindrome finder in Scala, but this one might take a really long time because I'm trying to get a whole bunch of values from this from a very long string. I can make this lazy by creating a lazy view on it. And so this makes that collection a lazy view on that collection. So it's a decorator for the collection rather than a fundamental part of the collection itself. And that's an example of working smarter and not harder. One of the things you'll find when you go to functional programming languages are common things that you're used to don't work the same way anymore. A good example of this are design patterns, which are you really used to in languages like Java and the object-oriented imperative world. But many of these design patterns don't really work anymore, not really applicable in functional programming languages. In fact, usually one of three things happen to them. The pattern is completely absorbed by the language, so the command design pattern is a good example of this. So is the strategy design pattern. The pattern solution still exists in the functional paradigm, but the implementation details are different. For example, the flyweight design pattern, which is really a caching pattern, is now trivial to do with memoization and a much cleaner, easier implementation with a lot less junk. Or the solutions implemented using capabilities that other languages or paradigms like for example, laziness. There are all sorts of things you can do with laziness in functional languages that obviously no design patterns exist for in the functional programming world. So imperative languages use state to model programming, exemplified by parameter passing and hidden context like this. And closures allow us to encapsulate both code and context and pass them around to a place that it is purely applicable to use. In fact, closures end up killing off about half of the design patterns that you typically use. So the last thing I want to talk about here is this pyramid. So back in 2006, I kind of accidentally repopularized this term polyglot programming in a blog entry that I wrote. This happens sometimes in Keynote. It's very persnickety now. This idea of polyglot programming, that we now have lots and lots of languages that run on the JVM, and there is no one true language to rule them all, and now it makes more sense to start mixing and matching languages a little more strategically. Along with that is this observation that a few years ago there was a lot of talk in the programming language world about what's more important in languages, static versus dynamic typing or strong versus weak typing. And after thousands of hours of arguments about this, I've pretty much reached the conclusion that this is really more developer preference than anything inherent about the capabilities of the language. And I think the much more important characteristic of languages we should be looking at now is not the typing characteristic, but rather how functional they are. And in fact, you can group these languages like this, where we have these really strong functional languages on the right-hand side. When I wrote my Polyglot Programming article, my colleague Bini made a really interesting observation that since we can now mix and match languages, that maybe we should think about building the most stable layer at the bottom and then a more dynamic layer as we get closer to the user, and then use more domain-specific languages as we get higher and higher to the top. And I think that's a good idea, but now I would say, rather than say stable, because it was kind of a suggestion that that's really static typing, I don't really think that matters. So in my updated world, the stable layer here is a really strong functional core that uses functional programming. And then as you get closer to the user and closer to things like user interfaces, use more imperative and object-oriented programming, because it's easier to store state on behalf of the user in sessions and things like that. But if you have a really strong functional core, notice that one of the things that we try to do in the functional programming world is minimize the amount of state that we mutate. Well, what are you doing when you write unit tests? You're checking to make sure that state got mutated correctly. If you have fewer state mutations going on, you have a smaller testing burden and you have a higher confidence in your code. That's why I think this is really going to be the core of the stuff we write. The really important stuff, the business rules, the validations, and those kind of things are going to get more and more functional. And then we'll leverage imperativity in objects where it makes more sense, where we really need to share state in places like UIs. I'm just a little bit over time because I started late, so we'll go ahead and take a break now. I'll be around for the rest of the day if you have any questions about anything, and you can download this from my website. Thanks very much for coming. Hope you enjoyed it. Thanks.